Thanks for tuning in, calculus students. These are problems that involve shifted axes, where the solid that results when you rotate a region around is not on one of the x or y axes. It's been shifted. So here is, we'll do a couple of examples here. The instructions are: find the volume that results when the region enclosed by the curves is revolved around the given axes. We're just going to set it up and show you kind of how it comes about. The first thing is to graph these. Y equals negative x squared. Okay, that's a parabola that's opening down. I'm just going to sketch it real fast right here. I hope that doesn't come back to make me do more work in the later. Y equals negative 1. Okay, I'm just going to bound that out. X equals negative 1. So there is that part, and x equals 0 is the y-axis. Our region is this little area right in there. Not quite it's not half of a unit. It's because there's a curvature in there. And we are revolving around the line y equals negative 1. So that dotted line that I've drawn right there, that is the line y equals negative 1. I'm going to make a little spin on there to show that we're revolving around that axis. So once we've done that, we've found it, then we kind of establish, okay, like we're spinning it around. You could, I'm going to amplify it here just to make it a little bit more clear. I'm looking at something like this. Let's see. Something like that. That's being revolved around this axis. And so what's going to happen is as that thing spins, it's going to create, I'm going to take a little tiny sliver there, it's going to create another solid that's made like that. What I've normally taught my students to think about is to project that sliver, that little dx, out here, and as we revolve it, it's going to create a disk. It's going to be like a solid disk. And that helps to kind of visualize, all right, even though that represents just one tiny sliver, there's going to be an infinite number of those disks stacked around, but that general disk should be allow us to kind of think about what the radius is. The radius of the disk, I'm just going to use small r here, is going to be this, wherever it is here, that function minus where it started. So you think of it as a number line. That distance is the farthest to the right of the number line minus the farthest to the left. So since we're going up here, and the farthest, like the most positive part is above, that is the line. Let's see, that is oh man, are we in? Yeah, it's y equals negative x squared. It is negative x squared, take away negative 1, because our axis there is y equals negative 1. So that distance is essentially negative x squared plus 1. That's our r. So now that I'm going to like kind of wave my hands, because I know we've been doing a lot of work on how the area sets up into the integral being the volume of revolution. It's pi r squared is the area of that disk. Here's the pi. The r is negative x squared plus 1 squared, and then dx is that little thickness that will create the volume. That is the setup for the integral of our volume. We're not quite done yet. We need to know what the limits of integration are. They are going to go, since we're looking at dx, we're going from the leftmost point, which is negative 1, to the rightmost point, which is 0. In this problem, it was pretty clear that those limits are right on our coordinate axes. There we go. Okay, number 2. Now, I'm assuming, yes, you can put that into your calculator or do the integration to find out, yeah, what's it end up being? Oh, I don't have the answers with me. Whoop. Okay, number 2, we are doing, x equals y squared plus 3, x equals 2. I'm going to set up, man, let's do the hard stuff first. If x equals y squared plus 3, it's hard for me to kind of think about, I know it's going to be parabolic, but it's hard to think about like, okay, where is the shift here? So here's what I do. If in doubt, kind of work it out. If x equals y squared plus 3, then x minus 3 equals y squared. And then if we take the square root of y squared, that's really plus or minus y is the square root of x minus 3. So that means the square root of x minus 3 is a square root function that has been shifted to the right 3. I'm going to, 1, 2, 3, 4, I'm going to sketch it in right here. That's the plus part of y equals square root of x minus 3. The minus part is just its mirror image. So I'm going to draw that in there. That, we've got our function done. X equals 2. Just going to like, right now we're bounding that region. Y equals -1 there, and y equals 0, which is the x-axis. It looks like our region is this in light blue. That's our region, and we are revolving it around the line x equals 2. Okay, we've already done that in a dashed line. That's the line x equals 2. So it might help to kind of think through if we're going to project this. That's going to be, well, I'll just do it down here. I'm going to take a tiny, oh, it's going to go revolving around there. So that means I'm going to take a tiny sliver, that's going to be a dy, and I'm going to revolve it around that line x equals 2. This is also going to create a solid disk. There's no space in this one. So our radius here is going to be the, think of it as a number line. We're going to look at that distance from here to somewhere here. It's a general look. So our radius is, it's going to be y, oh, let's see. Oh, you know what? X equals y squared plus 3. I already have it in terms of y, so it's going to be y squared plus 3 take away 2. That's our distance, which is equal to y squared plus 1. That's our radius. And so when we set up our integral, we're integrating in terms of y. It's going to be pi r squared, so that's y squared plus 1 squared dy. And our limits now of integration, we need to make sure that we are in terms of y, and we're going from the bottom to the top. By bottom, I mean -1 to 0, -1 to 0. That is an expression of our volume.